the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of a series of videos on matrix arithmetic for linear algebra and pre-calculus students. I say linear algebra students because you need this material for linear algebra. I say this for pre-calculus students because, well, sometimes you may learn this in pre-calculus. In this video, we're going to focus on the arithmetic properties of matrices. And this is a two-parter. We actually did part one earlier, and that was this guy right here. It's basically all the summation properties of matrices, right? You're adding a couple matrices or adding three matrices or possibly taking scalar multiples of matrices. So that was all part one. Part two, on the other hand, is all about products of matrices and some of their properties of the products of matrices. Let's go ahead and let A be an m by n matrix, B and C be the matrices of the same size for which the indicated operations are defined. And if you don't know what that means, you should watch the previous video in this series where I talk about when matrix products are well defined. It's something to do with the size of the matrices being multiplied. Anyhow, we have an associative property of matrix multiplication. A times the quantity B times C is the same thing as the quantity A times B times C. Again, as long as all of these products are well defined. That's a lot of possibilities. There are a lot of things that could possibly go wrong with that. But if it can happen, it is true that you can reassociate those products. You can also distribute matrix multiplication. So A times B plus C is the same thing as A times B plus A times C. The order of that is incredibly important, so I need to make a note of that right now. This is not the same as B times A plus C times A. So remember, I said it in the previous video, AB is generally not the same as BA. In fact, more often than not, it's not BA. So please watch out for that. Then we have the other distribution property, B plus C times A. Well, that's the same as B times A plus C times A. Again, that's not going to be the same as AB plus AC. A scalar multiple of a product of matrices, well, you could apply that scalar to the first matrix, then take the product, or apply the scalar to the second matrix and then take the product. And this last property I actually rewrote because I wanted to really drive home the dimensions here. The identity matrix times A is going to be A. Remember, A is m by n, right? So that is true, but that's actually equal to A times the identity matrix. However, if you multiply it in this order, the identity matrix here has to be an n by n identity matrix. So these are not the same sized identity matrices. But it is true that the identity matrix times A is A, and A times the identity matrix, again, as long as the matrix multiplication is well defined, is again just A. And I want to drive home again the fact that that's not actually telling us that matrix multiplication is commutative, because this identity matrix is not the same as that identity matrix. So it's not like, oh, B times A is A times B. No, it's not. Those two end matrices are not even the same size. So let's prove the associative property of multiplications. That would be this guy right here, just to showcase how this is done. So I start with the left-hand side. The matrix A times the quantity B times C. Well, we happen to know, by definition, the matrix B times C is actually the matrix whose columns are the matrix B times the respective columns of C. Now, I'm assuming here that C has n columns, so I should be very careful here. Maybe I should start with a statement about the size of the matrices. So let A be m by n, B be n by k, and C be k by p. That way the products are all okay. If that's the case, then C has p columns, not n columns, so I'll go ahead and change this out. However, that's just a product of two matrices. Again, what we have right here is just the product B times C. It's a single matrix whose columns are the matrix B times the columns of C. But again, just to drive the point home, that's like a matrix A times a matrix D, where D is just this big old matrix right here. But we happen to know by definition, a matrix times a matrix is, well, obviously another matrix, whose columns are the leftmost matrix times the columns of, in this case, D. And the columns of D are the following. So again, just to repeat, two matrices are being multiplied here. Actually, we're focusing in on this. Two matrices are being multiplied here. That product is the leftmost matrix times each and every single column of the right matrix. So B times C1, B times C2, and those are the columns of the product BC. But that's just some matrix we'll call D. And again, matrix times matrix, it's going to be the first matrix times each and every single column of the second matrix, and those form the columns of the product. So again, the matrix A times the first column of D, the matrix A times the second column of D, and so on and so forth down the line. However, we know from previous work that A times the quantity B times C is the same thing as AB times C. That is actually what we used in the last video, and so we proved that there, that a matrix times a vector is the same thing as the two matrices being multiplied then times the vector. However, this is now the matrix AB times every single column of the matrix C. That is, by definition, this is the matrix AB times the matrix C. And you can see that we have just proved associativity of multiplication for matrices. Again, I need to repeat this. In general, AB is not the same thing as BA when it comes to matrix multiplication. But other things I want to mention here. If A times B is equal to A times C, this is a property we take advantage of all the time in algebra. If 3 times X is equal to 3 times Y, then that means X must equal Y. That's what we take advantage of in algebra. However, that is not necessarily true in linear algebra. If AB equals AC, it is not necessarily true that B is equal to C, and we'll see that in examples. So be very careful of that. Also, if the matrix product AB becomes 0, it does not necessarily mean that A or B have to be 0. This is really weird about linear algebra. We are so used to if two objects multiply and become 0, one of them has to be 0. But that is not the case in linear algebra. In linear algebra, all bets are off. In fact, you could try it on these two matrices right here. This would be A and this is B. I hope you agree that neither of those matrices are actually 0, yet when you perform the scalar products of row 1, column 1, that'd be 1 minus 1, or 0. Now row 1, column 2, well that'd be 1, again, minus 1, which is 0. Row 2, column 1, well that again be 1 minus 1, which is 0. And row 2, column 2, again, 1 minus 1, which is again 0. So a very quick example that you could have two matrices that multiply to become the 0 matrix, yet neither of those two matrices need to be 0. Now, honestly, this is all I have in this video. The only reason why I wanted to make this a separate video was because I got tired of recording in the previous video, so I thought I'd just make this a separate one. Anyhow, I hope that at least this material seems somewhat okay to you. One thing I do want to drive home is this warning. Just make sure you're okay with it. AB is not the same thing as BA, and these other two properties as well. If AB is equal to AC, B is not necessarily equal to C, and if a product of matrices is 0, doesn't mean that either one of them has to be 0. Anyhow, I hope to see you in future videos, and I hope you have a wonderful day. Be a great human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.